I want to go back to the hydroxyl sink.
Okay, hydroxyl radical, yes.
Hydroxyl radical, right. And because that's something a lot of people don't know about. I mean, that is one of the major things that kind of eats methane and keeps it somewhat in check.
So the hydroxyl radical is it's OH radical, so it's not the microbes that eats methane.
I misspoke, but you know, it destroys the methane.
It's one of the biggest uncertainty in the global methane budget because the hydroxyl radical have a lifetime shorter than 1 second. So it's almost impossible to measure it directly, you know, over a very large scale, like global scale. And that's why we pretty much need to rely on other lines of evidence to tell us how big it is and how it's changing over time. And this is one of the biggest challenging in understanding the methane budget and understanding the recent trend in methane. And
is there any reason to think that the hydroxyl reaction is increasing or decreasing or staying the same?
So I saw that. So one of the other lines of evidence I said is those from what we call a chemical transfer model. In those models, you simulate almost every single reactions that could produce the hydroxyl radical in the atmosphere. And those models, typically they do not agree very well with each other. You can have like 20 different models and give you 20 different results. But overall, the overall average of the results give us something like a very small increasing trend in the OH, in this hydroxyl radical. So basically that says those models tell us that the methane sink is actually slightly increasing over a year. But the atmosphere, the methane in the atmosphere also increasing. That means that the emissions need to increasing even faster comparing to the case that if the sink is just constant.